Almost all the properties of differentiation is a consequence of the mean value theorem. So we will first prove the mean value theorem and then in a dedicated module prove the various consequences. Then in another module we shall see the most powerful consequence of the mean value theorem, Taylor's theorem. So let's begin with a simple lemma. Let f be differentiable on open interval a less than b, just to ensure that it's not the empty set. Suppose for some c in ab, f attains its maximum at c. What I mean by this is, that is, f of x is less than or equal to f of c for all x in ab. This is a point of maximum of the function f. Then f prime at c is 0. The derivative of a function at a point where it attains its maximum in the open interval ab is always going to be 0. And the proof of this is directly from the very definition of the Newton quotient. So let's take the derivative at c. So this f prime of c is nothing but limit h going to 0 of f of c plus h minus f of c by h. Okay. Now note that the numerator is always going to be less than or equal to 0. The numerator has to be negative. Why is that? Because the point of maximum is at c. So the numerator is non-positive. That's the correct way to say it. The numerator is non-positive. But the denominator could be positive or negative depending on whether h is greater than 0 or h is less than 0. So if h is less than 0, then the above limit is non-negative, because the numerator is non-positive and the denominator is negative. The quotient will have to be non-negative. On the other hand, if h is greater than 0, then the quotient, the Newton quotient is non-positive, because the denominator is positive whereas the numerator is non-positive. Therefore the quotient will have to be non-positive. The only possibility is f prime of c equal to 0. As you approach from the right and the left, the signs are different. Therefore at the point c, the only possibility is that f prime of c is 0. Okay, that was rather easy. We immediately get a nice consequence of this, which you might have heard is called Rolle's theorem. Rolle's theorem. Rolle's theorem. It says the following: let a b subset of R be an interval a less than b. Suppose f is continuous on the closed interval a b, differentiable on the open interval a b, and f of a equal to f of b. So you have a function which is continuous on the closed interval a b, differentiable on the open interval a b, and such that f of a is equal to f of b. The values at the endpoints coincide. Then we can find C in AB such that f prime of C is equal to 0. Proof. Again, the proof is going to be a straightforward application of the previous lemma. If f is constant, nothing to prove. Nothing to prove. Okay. Now suppose for some x greater than a but less than b, f of x is greater than f of a. We are assuming now that the function is non-constant. First, we make the assumption that at some point in the open interval ab, f of x is greater than f of a. Because ab is compact, f attains its maximum somewhere at some point C in the closed interval AB. But the endpoints, the values are equal, and we already know that f of x is greater than f of a. So in fact C must belong to the open interval AB. Because of this, the endpoints, the values are same. Somewhere in the interior at the point x, it's greater than f of a. There must be a point C in the open interval AB on which the maximum is assumed. Here I'm using the fact that continuous functions on compact sets attains its maxima and minima. Right? I'm just going to use the maximum. Then f prime of C is 0 by previous lemma. Okay. Now the other case is suppose f of x is less than f of a for some x in open interval AB. Then the previous lemma can be rephrased for minima. The same proof with a very minor modification will tell you that at a point of minima also the derivative is 0. Exact same proof, just slight modification for minima, and the above proof can also be modified. So this will be a pattern in even in this module as well as the next few ones, where I will just phrase it for one case. All the other cases are really straightforward, and at this stage you should be mature enough to be able to prove them on your own without even opening your eyes. Okay, so this is done, hence proved. So this is a geometrically obvious theorem, again that requires a proof. So this is what Rolle's theorem is saying. If you have the point AB and you have that the graph of the function returns to where it is. The way I have drawn it, f of a equal to f of b equal to 0, but that doesn't really matter. All this is saying is, if the values have to return, then the curve has to at some point become flat and turn. At that point, when you consider the tangent line and the slope of the tangent, that has to be 0. So it is proving something that's geometrically obvious in a rigorous way. Now we come to Lagrange's mean value theorem. Since this is going to be again and again used, I'll just abbreviate it as MVT so that there is economy. Let again f from AB to R be continuous and differentiable continuous, okay, to be, since this is an important theorem, I'm not going to leave out any hypothesis. Let f from AB to R be continuous on AB and differentiable on open interval AB. Okay, again A is less than B. Then there exists a point C in the open interval AB such that f of B minus f of A is equal to f prime at C times B minus A. Okay. Now this result might seem mystifying, and you can immediately dispel this mysticism by a simple picture. So suppose you have some function. Suppose you have some function like this. Now this result, if you have f of b equal to f of a, the left hand side is 0. Therefore this result is actually proved as Rolle's theorem when f of b equal to f of a. But we might not have f of b equal to f of a, right, in general. So what this is saying is, if you join this, the slope of this line, the slope is f of b minus f of a by b minus a. This is from high school analytic geometry. The slope of the line is given by f of b minus f of a by b minus a. Now what we are going to do is, we are going to view this function sort of as a graph over this line. We are going to view this function as a graph over this line and then apply Rolle's theorem. Okay, so all this is saying is, if I view this function as a graph over this line, there will be a point where the slope will be parallel. Okay, so if I am viewing this as a graph, that means that function's derivative at this point is actually 0. Fine. So this is a bit vague, but the proof will make it very clear what is happening. Proof. Now we want to apply Rolle's theorem. We want to apply Rolle's theorem to a new function. So we define g of x by definition to be f of x minus f of b minus f of a by b minus a times x minus a. Okay, so we have defined the new function g of x equal to f of x minus f of b minus f of a by b minus a into x minus a. Then g of a is going to be equal to f of a minus 0, which is f of a. Okay, and g of b is going to be equal to f of b minus f of b minus f of a. Okay, and this is equal to f of a again. This is equal to f of a again. So what we have managed to do is, we have managed to make g of a equal to g of b by subtracting this f of b minus f of a by b minus a into x minus a. Right? So actually, to illustrate the point that I'm going to make this a graph over this particular line, it's better to have subtracted a slightly different function, but this will do the job for us. Okay, now by previous lemma or previous theorem, that is Rolle's theorem, by previous theorem we can find C in the open interval a b such that g prime of c, which you can do the computation, is going to be f prime of c minus f of b minus f of a by b minus a is equal to 0. Or in other words, f of b minus f of a is equal to f prime of c into b minus a. So let me clarify one remark I made earlier, that this function will do the job for us, but a better function is to consider, I mean, we are done with the proof. I'm just going to make some extra remarks. So let me just put a box. So remark, the line passing through f of a and b f of b is the graph of L of x by definition is equal to f of a plus f of b minus f of a by b minus a into x minus a. Okay? This is actually going to be the graph, so L from AB to R. This L of x is actually the equation of this line, from A to B. Okay? So alternatively, we could have, this is almost exactly same as the function we subtracted, except one slight change will happen. If you consider f of x minus L of x, you would have landed up with the symmetric situation and call this the function g. You would have ended up with g of a equal to g of b equal to 0. Okay, you would have landed up with this nice symmetric situation where g of a equal to g of b equal to 0. That's the only difference. Fine. You could have applied the Rolle's theorem now and concluded the proof. So from the next module onwards, we shall see applications of the mean value theorem. This is a course on real analysis and you have just watched the module on the mean value theorem.